PhD presentation. Abdullah was born in Palestine, the West Bank in Palestine, and moved to a young age to Ohio, not Cleveland, but Youngstown, Ohio. And he went to Youngstown State University, got a engineering degree, and then he chose to come to Berkeley, and of all people, he chose to work in my laboratory. He came there as a fellowship, actually. He's been here for 5 years. He has been, well, you will see the quality of his work. Actually, in one of the presentations, an APS presentation, somebody asked him, what software you use to generate these lines? These are not software generated lines, these are laboratory real lines. So you should do that. Now, he will finish his PhD today, I hope. And then he has a whole bunch of things to do. Now, he wants to do the experiment. He's not content with what he has. He wants to do the experiment. He has to move to, he has a whole long list of things. To finish experiment, move to relativity space, is working. Also, along the way, get married. So take it away.
Thank you very much for the introduction. Before I get started, I just want to make sure, is everyone on Zoom, are you able to hear me and see my screen? If I can get an audible yes, that would be great.
Yes,
I can hear you and see your screen.
Yeah, we can hear you.
That's encouraging.
Okay, I'm going to assume that everyone can hear me and can see my screen. Okay, so welcome everybody. Thank you for joining me this afternoon. Today we'll be talking about the vortical flows over spinning disks and over over spinning cones and over a spinning disk at angles of incidence. So go ahead and get right into it. The contents of my work are going to include some introductory slides, some motivation slides. I'll go in review of the main experiments that we've used to study these flows. Mainly we use a smoke wire visualization technique, and we use planar particle image loss symmetry to take measurements of the flow fields. In part one, I'll be presenting the results and analyses of flows over cones, and in part two, we'll be looking at flows over a spinning disk. So to help motivate this, it's well studied in the literature that flows over cones, non-spinning cones at angle of incidence, result in these symmetric trailing vortices in their leeward side. And these vortices are symmetric, so all lateral forces, induced lateral forces, are neutralized. So this tends to be more of a favorable flow condition. However, when you introduce the effects of spin or a rotating cone, the symmetry is broken, and we expect to see unequal lateral forcing on the cone. This has strong implications on the trajectories of spin-stabilized bodies, hence why this is an important topic of discussion. And the literature seems to be constrained to zero incidence cases, there seems to be constrained to non-spinning cases where there's very limited information on the effects on the vortical flows for spinning cases. So in the bottom are some of the earlier flow visualizations done by Worley in a water tub. What he did was he injected dye at the surface of the cone. On the left is a top view, on the right-hand side is a side view. And we can see the formations of these helical patterns forming near the leeward side. Okay, this is basically what we want to expand on. We want to know, what does the influence of rotation have on this? Beyond the vertical flows outside of the boundary layer, the boundary regions have very complex phenomena as well. So the laminar to turbulent transition is an important topic because it has significant effects on skin friction and drag for incompressible flows. For compressible flows, it will have direct implications on aerodynamic heating, but everything here will be low speed incompressible. The laminar to turbulent transition is marked by these spiral wave instabilities, which are centrifugal and cross-flow instabilities within the boundary layer. So if we look here, these are some early flow visualizations of the boundary layer regions done by Kobayashi in 1983. And what he did was he coated the surfaces with a tetrachloride spread. And when this chemical makes contact with the free stream, it creates this very dense opaque smoke to help us visualize the boundary layers. So if we look in the first third of the cone near the vertex, we see very steady flow patterns. This is the laminar boundary layer region. There's a pinstripe formation. This is where the transition occurs. And then we have a transition to a turbulent boundary layer marked by these turbulent puffs of smoke. Now, if we take a cross-section of these pinstripe vortices, we can see that cross-section here on the right-hand side. They are composed of counter-rotating vortices. Okay. The literature is constrained to zero incidence cases where there's good agreement with theory, with stability theory. However, whenever the introduction of angle of incidence is incorporated, the disparity with theory is very clear. And there has been recently some more progress, including effects of zero incidence or of low incidence cases, but we're going to be studying the effects of larger angles of incidence. Okay, so my previous work has been published in the Journal of Visualization, Springer. And in that study, we studied and provided reference flows over a spinning cone of half angle 30 degrees. This serves sort of as a prelude for the more quantitative studies that I've done in the last 3 years for the remainder of my PhD, where the scope has been extended to include a wide range of half angles of cones and also to incorporate the measurements from Ph.D. So the half angles that we're studying range from 10 degrees all the way to the limiting case of 90 degrees. This half angle of 90 degrees, that corresponds to flow over a flat disk. So it has an asterisk. That's going to be treated as an independent study because the flow fields around the disk are quite different from what we see over cones. We study a range of angles of incidence between 0 and 36 degrees, and we use this rotational speed ratio. This is a ratio of the angular rotation rate at the base of the cone with the free stream. This parameter allows us to make one-to-one correspondences between each of the half-angle cones. So what we're doing is we're fixing our free stream velocity. The diameter of the base of each cone is fixed because we are fixing the lengths of each cone. And we use this parameter omega, or the angular rotation rate, to fix the rotation parameter for each cone. Finally, the Reynolds numbers based on the diameter or based on the length of the cone are all order 10 to the 4th. So we are dealing with incompressible and low speed flows. Okay, so I wanted to define some terminology that I'll be using throughout this presentation that will be useful in characterizing the flows in different regions. So first, I wanted to point out windward surface. That corresponds to the surface that is directly exposed to the incoming free stream. The leeward surface, that is the surface that is sort of in the wake region where slowed flows are expected to be present. If we take a cross-section of the cone and we take that cross-section, look at it over here on the right-hand side, when the cone is spinning, we see that the boundary layer flows are in the opposite direction of the incoming free stream. So here, this is a projected free stream to this AA cross-section plane. They're going to be in opposite directions on the in the co-rotating meridian. The boundary layer flows and the free stream are going to be aligned. And this is going to play a very important part in defining and characterizing the asymmetric vortex systems that arise. And finally, I should note, we're using a fixed Cartesian coordinate system for the PIV measurements that are fixed with the center line of the tunnel. We also use a Cartesian coordinate system that's aligned with the surface of the disk or the generator of the disk. This will be used for some boundary layer studies. And finally, we use a spherical polar coordinate system whenever we're referencing potential flow. So some information about hardware that we're using. All of our experiments are done in an open return wind tunnel. It has a 14:1 contraction ratio. Allows for speeds to 20 meters per second. And most importantly, it's able to sustain low speeds of at least 1 meters per second. And that's very crucial for the quality of smoke visualizations. The cross section of the test section is 82 by 82 centimeters, and it's 365 centimeters long. And I wanted to note that all of our test models are machined out of plastic ABS. They are sanded, polished, and coated with a satin black paint. The vertices of all the cone models are rounded to a 2mm radius. This is going to help prevent premature flow separation. The cones are spun by an AC servo motor that is under computer control. And finally, we have this rack and indexing apparatus that allows for a wide range of angles of incidence in 3 degree increments. Okay, so for the first set of experiments, we use the smoke wire technique, and this is going to give us a quick description of what that looks like. In essence, what we're doing is we're dropping a twisted steel wire pair through the test section. It's held in tension by a weight that's held outside of the test section. And we're dripping a 50-50 mixture of glycerin and water onto the twisted wire pair. Once it's fully coated, we heat the wire up with an AC rheostat with about 50 volts. And that's going to vaporize or generate these streak line patterns inside the wind tunnel. So the wind tunnel is fully on when this is being done. Once the streak lines are fully in the field of view, they're captured with a camera, a high-speed camera. So here on the right-hand side is a snapshot of me actually running this experiment. Some important things that we can find here are the lighting setup. So we use two light sources, an LED lamp source that illuminates the light from the front. We use LED strips mounted in the test section ceiling directly above the test model. High-speed camera is mounted here. Most importantly, the software is probably one of the most important parts of this. Shout out to Terry for taking this photo. Okay, so for all of the flow visualizations, we use ImageJ and open source software to do some simple image processing. Essentially what we're doing is subtracting the backgrounds from each of the images. So here, this is sort of a stepwise process. This is a sample background image, a sample raw image. This is the image after the background has been subtracted, and the final product where brightness and contrast is enhanced. Okay, so now let's talk about the experimental setups for particle image velocimetry. We use two orientations. We use oblique and streamline. So first I'll focus on the oblique measurements. So oblique measurements correspond to planes in the YZ planes. Okay. What we do is we inject micron-sized particles, DEHS particles, with a Laskin nozzle atomizer. These particles are illuminated by overlapping laser sheets generated from a dual pulse laser. This dual pulse laser is mounted on the test section, mounted on the wind tunnel ceiling above two linear stages. This allows for traversing along the X and Y directions, and precisely aligning the laser sheet where we want it to be. The laser sheets are turned into the test section through an acrylic test section ceiling, and images are captured by this high-speed camera that's mounted inside of the test section about 50 centimeters downstream. Note that the actual camera itself presents less than 5% blockage ratio. However, the linear stage setup, which is 100 centimeters behind the measurement plane, that's going to present about 7% blockage ratio. So moving forward to the streamline setup. So we're also taking measurements in the XZ planes. When we switch this orientation, essentially we're taking out the camera and linear stage setup, we're pulling it outside of the wind tunnel. And immediately we were met with these severe reflections from the surface of the cone. And so we were working with different ways of mitigating this. The technique that we landed on is known as the fluorescent dye filtering technique. What we did is we made a fluorescent dye mixture using rhodamine dye and polyurethane, and we coated the surfaces of the test models with that mixture, or with that paint. And what that allows for is any reflected light from that surface is emitted at longer wavelengths, which can then be filtered out with a bandpass filter. The bandpass filter is mounted in the C mount of the camera. Finally, now that we've pulled the camera outside of the test section, we have two layers of acrylic sheets that we're going through, and we're losing a lot of light from that. So in order to accommodate for the loss of light, we cut out a section in the test section window and replace it with a high efficiency anti-reflective glass window. And furthermore, we cut out a small slit in the test section ceiling to allow for no internal reflections with that acrylic sheet as well. Okay. Finally, for all of the PID images, we use a filtering technique based on the proper orthogonal decomposition of image matrices. Okay. And what this allows us to do is it allows us to pinpoint the backgrounds, the laser reflections in the backgrounds, remove them, and it allows us to visualize particles that are very close to the surface. And those are the regions that we're interested in. That's where these vortical structures are going to form primarily.
Is this also in-house open source software, or this is?
This is open source. It's published by Mendez. I should have said this as well. It's published by Mendez, and they provide it as a MATLAB package. And within this actual publication, they actually show validation of the method. And so it worked out very well. Okay, so that's all for the explanations of the experiments. Now I'll be primarily talking about results. We'll focus first on flows over cones. Okay, so for the first case, we're going to look at a slender cone half angle of 10 degrees It's not spitting, and it's at the highest angle of incidence case of 36 degrees. On the left-hand side are the flow visualizations from our smoke wire technique. We notice these very coherent vertical structures forming near the leeward surface. If you squint really hard, you might be able to see the interiors. There are actually interior sets of other helical structures inside that are fairly clean. Now, on the right-hand side is a sample oblique Ph.D. measurement. So we're taking velocity measurements and we compute vorticity. And here I'm plotting the vorticity contours. This allows us to characterize the topology of the vortex systems if we take a cross-section. So this corresponds to YRD is equal to 1.0T. That corresponds to a plane that's about center of this cone. One thing to note that we see here is there's symmetry in the actual scaling of the vorticity on both sides of the Z plane. Furthermore, we see that there are these primary vortices, secondary vortices, and tertiary vortices. So 3 vortices are forming on each side. There's a slight asymmetry in the setup. This could be a result of slight offset of the actual measurement planes and potentially some asymmetry in the upstream flows. However, as we get further along the length of the cone, the local flows overcome these asymmetries, as we'll see in the future. Please come on. So if we take a set and look at the same sort of analysis over a cone of half angle 15 degrees, slightly larger, we see the same flow patterns, the same flow behaviors that we've seen before. In the cross section, we see more clearly the formation of these symmetric vortex triads. And also we start to notice these sort of regular wave patterns forming in the streak lines near the surface. And we suspect that these are signatures of boundary layer instabilities. So we continue this process for the larger half angles cones. And we note that as you continue to increase, we're going to go 22.5, 30, 45. For the sake of time, I won't do that to you today. So this will be the final case. But again, we see these very coherent vertical structures. We see these secondary sets of helical structures as well, and also a tertiary helical pattern here. And that's in agreement with the vorticity contours that we reveal with oblique Ph.D. So to sort of wrap up the symmetric vortices behind leeward cone or behind cones, these are the terms that I'll be using from here on out. So we saw that the formations were forming in symmetric vortex triads that were each composed of primary, secondary, and tertiary vortices. This prevailed for all half angles of the cones that were non-spin. Furthermore, it's well studied that the formation of these primary vortices arise from shear layer mixing of the incoming high-speed flows and the latent flows near the leeward surface. As those primary vortices are formed, they propel themselves down towards the surface by their induced velocities. And as they're doing that, they're producing these secondary vortices that are counter-rotating due to the viscous effects. Now, I'd like to conjecture that as these secondary vortices are formed, they're breaking apart the primary vortices and generating this tertiary vortex, which is the same vorticity sign as the primary vortex above. This is a new piece of information. I don't have all the information I need to make that as a final conclusion, but that's what I would like to conjecture. On the right-hand side is an isosurface plot that is composed of 34 measurements along the length of a cone that are half a centimeter apart. Values in between the measurement planes are cubically interpolated. And this just serves as a visual aid as to what this vortex system looks like from behind. So now I want to actually compute the vortex strengths. The way that we characterize the vortex strength is through a parameter known as circulation. And circulation, which comes from Stokes' theorem, is essentially the area integral of vorticity. Okay, and so numerically what I'm doing is I'm summing the product of the vorticity points and the cross-sectional areas, which are essentially the vector spacing squared. And I'm doing that for both halves of these images to compare between the gamma left and gamma right to one, show that there's actually symmetry between there in the actual quantitative values. Once I have gamma left, gamma right, I sum those to get a gamma total, which corresponds to the total vortex strength of one slice. We sum those along the length of the cone. So all of the slices that we've made along the length of the cone, we sum those to get an idea of sort of the vortex strength associated with one cone at one particular angle of attack. And finally, that corresponds to a Reynolds number based on circulation. A lot of words, but this will be very important in describing the following plots. So here what I'm plotting are the vortex strengths that are non-dimensionalized by each diameter of the cone and the free stream velocity. And we're also plotting the corresponding Reynolds number, the scale of the Reynolds number. So one trend that we notice is that as the angle of attack is increased, the vortex strength increases. This follows for all half angles of the cone, except in this case here for the slender cone, where we get a drop off. This drop off is associated with that vortex system leaving the field of view. Furthermore, we see as the half angle of the cone is increased, the vortex strengths are beginning to decrease. And this makes sense because as the half angle is increasing, it's approaching the geometry of a disk or a blunt body, and we don't really expect to see a lot of lifting forces there. And we know that lift forces are associated or comparable to the circulation.
These are all on a smooth cone, right? So
These are also
what's the roughness and so you measure the roughness and how are these smooth?
So the cones are, they're sanded, polished, and coated with paint. However, since we're dealing with low speed flows, the order of that surface roughness with the order of the boundary thickness is negligible. So we didn't actually provide measurements for surface roughness. Another parameter that I forgot to mention in the previous things is I've noticed that as the half angle of the cone is increasing, the vortex triads are starting to form at further distances, further horizontal distances. And so I computed that value, and I'm calling that non-dimensional value PS. And we see that as the half angle of the cone is increasing, we see that that value, the distance between the vortex triads is increasing. The way that I actually got these values, I took an arbitrary slice at say y over d is equal to 1, and I measured the distance between the centers of the primary vortices, and that's what I take as the value d, and then I non-dimensionalize that value by the diameter of that particular. Finally, another interesting parameter is this non-dimensional separation angle. Essentially, we're non-dimensionalizing the separation angle with the half angle of the cone. And we notice a trend in the red plots here. As the half angle of the cone increases, the separation angle decreases. So I just wanted to note that this distance, this sort of relationship is going to play an important factor in the asymmetric vortex system.
Can you say what the separation angle is?
Yeah, so the separation angle is the angle of incidence where we see flow separation at the leeward surface of the cone. So a rough estimate is if the cone generator or the leeward surface is directly parallel with the free stream, you should expect to see some flow separation happening.
So the distance between measured vortices, wouldn't that depend on where you chose to take the plane?
Yeah.
Because if you took it further apart, the relation might actually be stronger. Wouldn't it be better to take the angle rather than the?
That's a good idea. What I did try to do for accommodating for that is I took a fixed location, y over d is equal to 1 for all cases. And that's non-dimensionalized based on the diameter of each cone. But looking at the angle, that might be another way of seeing it. Qualitatively, you can actually see the separations. Okay, so go ahead and move on. How am I doing on time?
Oh, yeah, don't worry about that. Yeah, after all this.
12:39. Okay, I'm holding you hostage. So we'll go ahead and move on and see the effect of spin. So proceeding with the same sort of structure as before. Here's a slender cone, half angle of 10 degrees, that's rotating at a ratio of plus or minus 2 at an angle of incidence of 36 degrees. We're spinning the cone in plus and minus directions in order for us to be able to see both the co-rotating and counter-rotating meridians. And so on the left-hand side is co-rotating, right-hand side is counter-rotating. That's going to follow the same structure for the following slides. What we notice is a very coherent helical pattern forming in the counter-rotating meridian. It has a sinusoidal wave pattern. It exhibits a sinusoidal wave pattern. And this frequency of the sinusoidal pattern matches the angular rotation rate of the cone. And so this is an artifact of a slight misalignment of the actual cone central axes with the axes of the servomotor. However, we notice that this vortical structure is still able to sustain its integrity, even with these cyclic perturbations. On the right-hand side, we can actually see the topology of these vortical structures. We see the strong vortex that we see in the counter-rotating meridian that's very prevalent in the contour. We also see these red regions of vorticity that we suspect to be associated with other vortices forming in the co-rotating meridian, which unfortunately we can't see here. But if we increase the angle of, if we increase the rotation parameter from ±2 to ±3, we're actually going to start to see more details. So like we saw before in the counter-rotating meridian, we see this very strong vortex that gets separated from the leeward surface of the cone. But what we also see is a second set of helical patterns forming beneath it. It's a little hard to see exactly where this pair is forming from, or where this helical structure is forming. And if you take a very close look at the co-rotating meridian, what you actually can see is these helical patterns forming near the vertex of the cone. So that vortex is getting pushed into the direction of rotation. It's getting pulled into the counter-rotating meridian and out of the field of view in this particular case. Okay, and we see, again, this strong vortex in the contour, and we also note that it's quite separated from the leeward surface. So with this new behavior comes a new characterization, and I wanted to define some new terminology that I'll be using to help better discuss what I'm talking about here. So I'm going to define the vortex triads that are forming in the co-rotating meridian as cyclonic vortices. I call them cyclonic because they're rotating in the same direction as the cone. And similarly, the anticyclonic vortices forming in the counter-rotating meridian, they're rotating in the opposite direction of the cone. We notice from the behaviors of the series of PIV measurements that cyclonic vortex is getting pulled into the direction of rotation into the counter-rotating meridian, and it's actually getting sucked beneath the anticyclonic vortex, triggering its detachment from the leeward surface. The anticyclonic vortex, it appears to just continually grow in strength as it progresses along the length of the cone. And what I've done is I computed the actual vortex strength by taking an area that encapsulates just the primary vortex, and I plot those values here. We see a nice trend as we progress along the length of the cone. That strength is increasing. Furthermore, with an increase of angular rotation rates, we see a slightly upward shift of those values. And so that's because in this region between the anticyclonic primary vortex and the cone, there's a co-flow region there. The direction of the boundular is rotating in the same direction as the bottom portion of that vortex. So it's sort of feeding into the vorticity of that primary vortex. And this is sort of just a snapshot, a sequential snapshot along the length to show how that primary cyclonic vortex is getting pulled into the direction of rotation, sucked between the anticyclonic vortex and detaching, allowing that anticyclonic vortex to detach. And we'll see how that progresses. So now if we bump up to a half angle of 15 degrees, we see a completely different set of behaviors in cyclonic and anticyclonic vortices. One, in the co-rotating meridian, we see clearly that there's a coherent structure that remains in the field of view. It detaches from the leeward surface, and it's marked by these small scale rolling wave patterns that we think are associated to centrifugal instabilities within the boundary. In the counter-rotating meridian, we also see a new behavior. We see that the anticyclonic vortex stays close to the surface of the cone. At a finite distance from the vortex bursts, and it leaves behind it turbulent patches of smoke downstream. Also note that we see these regular wave patterns also forming in this spinning case. Again, these are signatures of boundular instabilities. Now we can look at the actual contours, the topology of this vortex system. We see the detached cyclonic vortex. So this red region corresponds to what we're seeing here. This blue region is the anticyclonic vortex that follows the surface of the cone. That's the vortex pattern that we're seeing following the direction of rotation.
Could you comment on is that getting like a lighting issue, or is that something really in the flow? Or
yeah, so are you talking about the black marks here?
Yeah.
Yeah, so these black marks are artifacts of background subtraction.
Okay.
So it's not real.
Okay.
And if we continue with larger half angles, we see that the same behavior is persisting. So this is the 22.5-degree cone. We see these regular wave patterns forming in streaklines near the surface. We see these small scale disturbances to the cyclonic primary vortex that's detached. In the anticyclonic vortex, we see that it follows the surface, it bursts and leaves turbulent pouches downstream. What's also pretty interesting is that we can see the cyclonic vortex actually forming in the co-rotating meridian in this field of view. So we can actually see both vortex pairs. So this is just a summary characterizing the asymmetric vortex systems for half angles greater than 10 degrees. We saw that the cyclonic vortex readily detaches from the leeward surface. It never makes it into the counter-rotating meridian. And we speculate that that is an artifact of those vortex triads forming farther apart from one another for larger half angle cones. And so since they're forming farther apart from one another, it's not going to be as influenced by the induced flows of the anticyclonic vortex. And that's why it never makes it over into that meridian. Furthermore, the anticyclonic vortices, they stay really close to the surface. They continually grow in size until they collapse. This is another isosurface plot constructed in the same manner as before. Gives a nice visual representation of what this system looks like from behind the cone. We see this detached cyclonic primary vortex. We see this tertiary vortex that I don't really talk about too much in my work, but it sort of just goes along for the ride. And finally, the anticyclonic primary and tertiary vortices, these stay close to the surface of the cone and continue to grow. As they stay close to the cone, surface of the cone, they're continuously being fed by vorticity from the adjacent shear layer. And that's why I'll get into that. So if we look at the vortex strengths of cyclonic and anticyclonic vortices, focus on this plot here. The anticyclonic is marked in blue. We see the vortex strengths are growing. Unfortunately, our field of view does not capture the vortex bursting events. So we just see the first sort of portion that we saw in the smoke. The cyclonic vortices, they begin to grow in strength, but then they cease to grow in strength at a particular finite distance, xt. And that's because that cyclonic vortex is getting kicked away from the leeward surface. It's no longer being fed by that adjacent shear layer. And that's why it's no longer growing in strength. And this same trend is seen for larger half angle cones, 22.5, 30 degrees, and 45 degrees. I have it presented here.
For the anticyclonic force, do you expect the current to also saturate or just leave?
So I expect that with the vortex bursting event, that there will be a loss of vortex strength. Okay, I just wanted to leave a few comments on the persistent signatures of boundary layer instabilities. These are sort of the angled wave patterns that I've indicated. And also, we've noted that for streaklines that get ingested deep in the boundary layer region, they're following the direction of rotation. So if we look at these arched or arced streaklines, these are following the direction of rotation because they're nearly attached to the surface. They're marked by these very small scale curly signatures. And these are signatures of the spiral wave instabilities that we expect to see. Furthermore, we see these for all half angles of the cones at angles of incidence greater than the half angle, or when the generator of the cone is aligned with the free stream. What's really interesting is that we saw these wave patterns for non-spinning cases as well. And so we suspect that these angled wave patterns are, so it sort of indicates that they are cross-flow instabilities, whereas these sort of squiggly patterns on the streak lines are spiral wave instabilities. Furthermore, these sort of rolling wave patterns at the leeward surface that mark the detached vortices, those are also signatures of spiral wave instabilities. Unfortunately, we weren't able to resolve this with PIV. However, these flow visualizations should serve as motivation for more future work to be done with this. Okay, so that concludes this portion of the talk. From here on out, I'll be talking about flow over a disk, time permitting. Are there any questions before I move on?
Can you comment on as you increase the angle of attack on the cone, how the boundary layer separates and goes into the turbulent regime, like at what distance does it separate?
I see. So if we go back to Kobayashi, it's a better description, right? But as you progress along the length of the cone, the transition from laminar to turbulence are governed by two parameters, the Reynolds number, the local Reynolds number there, and the rotation parameter. So as you're progressing along the length of the cone, the diameter is increasing, hence your Reynolds number is increasing and your rotation parameter is increasing. And so at a particular location of S in Reynolds number, you have this transition, and beyond that, it becomes turbulent. I wasn't able to characterize fully from our streetline images where that happens, but we gave some convincing evidence that there's something interesting going on.
Do you know if it matters much that your trailing edge is sharp? Or does that influence the flow on the surface of the cone at all? Or
I would suspect that the sharpness does have an influence, but I would note that I observed that the streak lines kind of can consistently have their integrity as the upstream flows. So they're not being abruptly affected by the sharpness of the base.
Yeah.
If it was rounded, I think that there would actually be some curvature in the streak lines.
or even if the whole thing you mounted on would actually extend without, it looks like it's much smaller than the cone.
Right, right.
Right.
Yeah, the cone motor is here.
But is there a lot of flow and turbulent behavior in that right behind the edge? Or
So unfortunately, yeah, from these pictures, you can't see it. I suspect a circulation region there, but the streak lines are not getting pulled into that region, so we really can't visualize it from the experience. But yeah, I suspect circulation regions, probably some turbulence, because we have some irregular geometries. But okay. So moving on to flows over disks. This is a natural continuation of the work over cones. It's a limiting case. So let's just talk about some of the well-studied characteristics of flows over circular disks. It's well known that the wake regions consist of these interlinked chains of irregular vortices that are shedding off of circular disks that are either at zero incidence, corresponds to normal flow, or inclined disks. And so a nice way to actually visualize this was done by Cal Wirth with a streakline visualization technique. Here is a sort of side view. The circular disk is inclined at some angle here, and here is a top view. And I wanted to sort of highlight these regions here. These are the interlinked chains of irregular vortices that are being shed into the wake region. The literature seems to be constrained within the wake region. And so our work is going to focus more on the upstream effects and try to pinpoint the sort of origins of these vortices. But beyond the wake regions, there's been a lot of work done within the boundary layers. Again, centrifugal and cross-flow instabilities persist. Professor Savaş has actually done some flow visualization studies of rotating flows over stationary disks. This is known as classical Baudouin flows, where circular waves and spiral waves are visualized depending on the Reynolds number of the disk or of the rotating flow. Also, similarity solutions exist that rely on numerical solutions for flows over axial flows over spinning disks, and for flows over inclined disks. So we're using the same hardware as before, except now we're using a disk. I just wanted to note that we're defining these radial velocity component as u parallel and this axial velocity component as u perpendicular. And that is with respect to the Cartesian coordinate system that's aligned to the upstream surface of the disk. Because of the three-dimensionality of this flow, we use a second set of another camera angle. So we're mounting a GoPro Hero 3 Plus into the test section, and this allows for an inclined upstream viewing angle of the disk that will be a nice tandem with the other streetline images. So getting into the actual flow viz, here is the most simple case of flow over a circular disk, not spinning at zero angle of incidence. We see immediately the formation of these coherent vortical structures forming near the central axis of the disk. And it's hard to see in this field of view, but if you look on the GoPro field of view here, we can actually see those vortices forming at the central axis. Once they reach a finite size, they get shed in the plus or minus y directions in a seemingly random fashion. By computing the actual frequency of shedding, we see that that matches Cal Wirth's experimental studies. And so we are confident that these are related to the interlinked chains of vortices that are being shed into the wake regions. Now, as we increase the angle of incidence, we see the same persisting behavior. We notice that the stagnation point is starting to progress towards the leading edge of the disk. We also see this primary mode of vortex shedding in the plus or minus y directions. But at the highest angle of incidence case, the primary vortex, so we still see these vortical structures forming, but they're forming at much smaller sizes. And instead of being shed in the plus or minus y directions, a soliton forms near the leeward edge and traverses along the direction of the free stream into the wake region. So I just wanted to identify, these are the two modes of vortex shedding that we have observed from the flow visualizations below. For angles of incidence less than or equal to 18 degrees, the primary mode of vortex shedding was in the plus or minus y directions, where we observed these coherent vortical structures forming near the central axes. Once they reach a finite size, they're shed back and forth in the plus or minus y directions. And at angles of incidence greater than 18 degrees, we see the soliton mode of vortex shedding. And this is just a schematic of what this entails. One thing to note is that the shedding frequency for the soliton mode of vortex shedding is nearly double than the first mode that we looked at. So now we want to address the effects of spin. So we're looking at the zero incidence case, rotation parameter of plus or minus 2. We see these signatures of centrifugal effects. So we still see these coherent vortical structures forming, but they're affected by these small scale centrifugal wave patterns. If we persist and we continue to an increased angle of incidence of 18 degrees, again, we still get these coherent vortical structures forming, but they seem to be getting diminished by these signatures of cross-flow / centrifugal instabilities. And at the highest angle of incidence case, we lose that primary mode of vortex shedding. We have a soliton mode of vortex shedding. It is amplified, and the frequency matches the angular rotation rate of the disk. Okay. So these are just some snapshots of.
You change the rotation speed and keep matching it. So it's locked in.
I would suspect it did, but I didn't actually do that. So here are just some snapshots of these centrifugal effects that leave these cross-flow signatures. These are reminiscent of the classic Kelvin-Helmholtz shear layer instabilities. We see these present in all angles of incidence less than or equal to 18 degrees. Beyond 18 degrees, we see this soliton mode of vortex shedding. So now I just want to talk about some of the measurements that we made. Question?
I guess what is it about 18 degrees? Like, is there, if you change the geometry, make this bigger, smaller, like things like that, would that change? Is there some way to predict 18 as a number?
Yeah, so one way to think about it is as the angle of incidence is increased, the disk is presenting less abstraction to the free stream. So it's kind of transitioning from a bluff body to something that's more streamlined. I haven't really dove too deep into that. Okay, so for the measurements here, I'm presenting velocity magnitude plots of the zero incidence case. On the left is the non-rotating case. These correspond to spinning cases. One of the drastic differences is we see the effect of the centrifugal effects pulling in higher speed flows closer to the surface of the disk. This is expected from theory. And also we note that the plus or minus omega cases are nearly indistinguishable from each other. And this makes sense. This is expected because we're just taking measurements of the same measurement. We compare our streamlines from Ph.D. to the potential flow, incompressible potential flow solution that is shown here. And we see that the streamlines from Ph.D. are in great agreement with our with our Ph.D. streamlines. However, a growing disparity arises with our streamlines as expected because our flow is very unsteady. There's a cyclic shedding of vortices and a constantly changing boundary layer thickness. So that's why we have this growing disparity with our streamlines. If we look at the velocity magnitude plots for increased angles of incidence, we see that the the speeds are getting closer to the free stream. Again, this kind of tags on top of, as we're increasing our angle of incidence, our disk poses less obstruction to the free stream. It's more streamlined, we have higher speeds closer to it. And this persists as we increase the angle of incidence to 36 degrees. So finally, we wanted some way to gauge our measurements with existing numerical and analytic solutions. So one way of doing this is we're measuring the slopes of the radial velocity components with respect to x and the axial velocity components with respect to z. And these slopes are directly correlated to the strain rates that are associated with the axisymmetric stagnation point flow solution. We see that for the zero incidence cases, the slope is decreasing, kappa x is decreasing with increased angle of incidence, and kappa z is increasing with increased angle of incidence. So what does that mean? So if we look at the axisymmetric stagnation point flow, the strain parameters that we are what we're talking about are these constants in front of our coordinate system, our disk-aligned coordinate system. AX corresponds to just these A values, and AZ corresponds to 2 times A. So if we have a perfectly axisymmetric stagnation point flow, the ratio between AZ and AX should be precisely 2. And we see from our measurements that it's about 1.97, which is in good agreement. As we progress with increased angles of incidence, we see that that ratio is decreasing. And we suspect that with an increased, or with a decrease in this ratio, the flow field is transitioning from an axisymmetric stagnation point flow to one that is elliptically asymmetric. Finally, we can compare the radial velocity profiles to incompressible viscous flow solutions a la Hanna. Hanna essentially defines this dimensionless rotation parameter mu, which is equal to the angular rotation rate and the strain rate. So mu corresponding to infinity, that corresponds to von Karman flow. That's an infinite disk spinning in a quiescent fluid, a still fluid. Mu is equal to 0. That corresponds to the classical Holman flow. That is just stagnation point flow over a non-rotating, non-spinning disk. Everything in between is a different ratio of angular rotation and strain. And our measurements falls between Karman and mu is equal to 2. So mu equals infinity 2, 1, 1/2, and 0. That comes straight from Hanna, and this is our contribution. On the right-hand side, I'm doing an overlay of the scaled radial velocity profiles over the non-spinning cases and a range of angle of incidence. And I'm overlaying them with the Holman solution, and as well as the rotating mu is equal to 4.3, corresponding to our experimental flow parameters. We see good agreement there. One thing to note, in all of our experimental measurements, we see these wavy patterns in our radial profiles, and we suspect that these are related to the cyclic vortex shedding there. These are time averaged, and they're still persistent in this. This is a closing remarks slide, which I'm not going to go through, but summarizes what I've talked about today. And I just wanted to take a brief moment to thank everyone who's helped me along the way. Everyone who has contributed. There have been many people who have contributed. And for those who didn't make it to the slide, you know who you are, I know who you are, and thank you.